All right, great. Thanks, Ada. Hopefully you all can hear me and see my screen okay. I assume Amarnath will let me know otherwise. So I'll give a brief update on the NGL project today with my 15 minutes, and certainly welcome any questions you have toward the end. Got to get this working. All right, so here's the introduction of the project, some of the innovations that we've made during the project, which is actually kind of toward the latter stages now. We have a report due in February next year, so we're working hard on finalizing that. So some of the innovations, we have a relational database. This is a MySQL database where all of the NGL data are stored. It's up to a few gigabytes of data now. It's a lot of data for somebody to try and download and work with. So we've also facilitated some interactive tools for people to work with the data in the database in the cloud. And we have a whole new class of case histories. So these are different from, or in addition to the case histories that have been used historically to build liquefaction triggering relationships. We've also been doing some supporting studies. So we can't fully constrain all of the effects of liquefaction using case history data alone. For example, we don't know if a particular soil maybe didn't manifest liquefaction because it can't, because it's not susceptible, or because it just wasn't shaken strongly enough. So we have some extra effort to get those things, including vertical effective stress or K-sigma effects. And we're now working on the formulation of an updated triggering and manifestation model. And I'll focus a lot of my attention today on that. Here's the project structure. So I just want to show this to show the number of people who are involved in the project. We have now quite a few different model development teams. So the top one, the SMT, is the supported modeling team. We're being funded by the U.S. Bureau of Reclamation through the Southwest Research Institute and NRC to develop this model. But quite a few other teams have joined in to use the NGL data and developing their own models, and we coordinate meetings with them monthly. If you go to nextgenerationliquefaction.org, this is a picture, a screenshot of what our tool looks like. It's a web interface built using HTML and PHP. All those beach balls are different earthquakes that have produced observations of manifestation of liquefaction or not. And we also have sites. If you click on one of those little orange or yellow balls, it will kind of explode out and have a whole bunch of data there. So you can certainly use this interface to go plot data. You can download it in CSV format from there. Here's a kind of more zoomed in one of the Loma Prieta earthquake. So this is an event, and those little pins are sites. And then there's a map of Moss Landing down kind of south of the earthquake epicenter there. We have in situ tests, including boring logs, cone penetration tests. Then we have observations. So there's the sand boil there on the right side. We also have quite a few locations, maybe about in the 20s, of sites that have a ground motion surface recording accompanying an observation of liquefaction. And you can see a sudden change in frequency content when liquefaction triggers in the spectrogram of that motion there on the sort of the bottom. This is the approach to the Bay Bridge. And there was liquefaction observed at this approach during the Loma Prieta earthquake. And so those red pins are cone penetration tests that have been done, and the blue pin is a borehole. And then we also have black pins that are observations, and that's where somebody went to take a picture or document cases of liquefaction. So there's the boring, the CPT, and then the observation, you know, it says settlement on the east side of the administrative building and so forth. And you can plot boring logs. These are SPT blow counts, and then cone penetration test data there on the left side as well. All right, so you can go to our GUI, that's nextgenerationliquefaction.org. NGL.org was already taken by natural gas company, so we weren't about to buy that from them. And you can also connect to the NGL database through Jupyter Notebooks on DesignSafe. So every day the database is replicated to DesignSafe, where you can build a whole workflow that queries the data using SQL to get out whatever information you want. It's a little more efficient than going through our interface and downloading CSV files. If you're going to be writing queries using Jupyter Notebooks, you need to understand the organizational structure of the database, like which table names to include in your query. And we have that information all available at this URL, the schema. The schema is just the organizational structure. It tells you which tables are in the database and how those tables are connected to each other through keys. We also have some documentation of different queries. So we recognize that interacting with data in a relational database by writing your own queries is not something that a lot of civil engineers may be familiar with. So we try and make it as simple as possible by providing some examples. These examples could even be used as kind of the building blocks to develop your own workflow. And we try and make it like the elemental blocks there. We also have a YouTube channel. We've had some webinars and so forth, and including one on creating Jupyter notebooks to interact with data. So if you go to Design Safe in the upper left, there's that little workspace button. And if you click that button, it'll pull down a drop-down menu and you can click on use cases, and then it will take you to a page where you can click on this. This is our NGL use case. And there are links to the Jupyter notebooks that you can find there, and a link also back to the GUI and the database. So this is an example of the simplest possible query you can do in one of these Jupyter notebooks. And so it shows on the top, the cell up there is, let me turn on the laser, right? This first cell is just installing a package that allows you to connect to the database that's hosted on Design Safe. This first line imports that package as NGL, and then I write a straightforward SQL query, select everything from the site table, and then I run this command that's part of that package in read SQL, and then I put in that string, and it gives me a pandas data frame that has all of the sites. This is a little old, but you can see there's 303 sites in here. Its indexing starts at 0, and they're all named and everything. You have latitudes and longitudes and all that. We have other examples that get a lot more complicated, including widgets and drop-down menus and plotting. So if you're interested in developing these workflows to work with the data, let me know. We'd be happy to help you out if you're having trouble with anything or find the documentation to be less clear than maybe it should be. So, all right, let's talk now a little bit about our philosophical approach to developing this model. So we'll first talk about the difference between triggering and manifestation. So what in the database, what we have are field observations of whether surface manifestation happened or not. So people go to a site after an earthquake and they say there were ground cracks, there were sand boils, maybe there was structural settlement or settlement of the ground surface or lateral spreading, and that all gets documented and it's in the database. Or really importantly, those things didn't happen. This is a site where nothing happened after a strong ground shaking. But analysts may want an actual triggering model. So it's possible that a soil layer might liquefy in that its pore pressure reaches a very high level, but it doesn't manifest. Maybe it's too deep in the profile, maybe it's dense, maybe it has a very strong crust and it just doesn't show up at the surface. So one thing we want is a triggering model, or some people call it a true triggering model, to distinguish it from past models that are really more manifestation models. And then we want a manifestation model too, right? So if a layer triggers, will anybody know about it? Is it going to form ground cracks and lateral spreading and sand boils and stuff like that? So then that brings us to the traditional approach. The common historical interpretation would be that if a site manifested liquefaction, it would be plotted as a solid symbol, and it might be above some threshold line that will separate triggering from non-triggering, or manifestation from non-manifestation. And we would interpret that as being 100% that this probability that this site triggered because it manifested liquefaction. And conversely, the probability of that the layer didn't trigger, even though it manifested, would be assumed to be 0. That's not necessarily true. You can get sand boils without reaching 100% excess pore pressure ratio. Then here's no manifestation. So there's an open symbol above the curve. This would be a false prediction in this case. And we would assume that since it didn't manifest, that's a site that also didn't trigger. So the probability of no triggering given no manifestation is 100%, and the probability of triggering given no manifestation is 0. So this has an impact on the position of the curve and also its uncertainty. And so the way we're approaching it is to use Bayes' theorem to try and separate out triggering from manifestation. And this is an expression showing the probability that a site has triggered given that there was manifestations of liquefaction. There's really 3 components here. There's the probability of manifestation conditioned on triggering occurring. Then there's the probability of manifestation conditioned on no triggering occurring. That would be like maybe a site that forms sand boils at an excess pore pressure ratio of 0.8. And then there's the probability of triggering, P of T. And so our approach is been to use all of our knowledge about laboratory tests to help us constrain this probability of triggering. We recognize that laboratory tests are generally disturbed. There are some frozen samples that have been done that are roughly undisturbed, but why not use all this laboratory data that we have at our disposal to constrain this, at least to provide a prior probability? And then we are regressing the probability of manifestation given triggering. So here's an example site that we can apply this to. This is Wufeng site A, which did not exhibit surface evidence of liquefaction, even though it was shaken very strongly during the 1999 Chi-Chi earthquake. Here's a zoomed in view that just shows some of the layering that we've interpreted for this site. And we've come up with some criteria to figure out which of these layers is most likely to manifest or most likely to be the critical layer. And you can see this darker green layer down here receives the most votes from the different criteria that we're using. I don't have time to talk about all those criteria. This is the one that the algorithm that we've developed and kind of our judgment too would assign as the critical layer. So when we start thinking like, okay, why didn't this layer manifest liquefaction? It has a fairly low I sub C below 2, indicating that it's a sand-like material. QC1 NCS is down here at around maybe 80. So that's pretty low. I would say this layer probably liquefied. But then you have this very thick crust, of thick cohesive crust up here. So it probably liquefied and just didn't come to the surface. And so that's low QCS, low I sub C, saturated soil. And so this is an open circle right there. That's where this particular point plots. And we looked at it because it's kind of an outlier. And so if we assume that the probability of triggering is 90%, and the probability of manifestation given triggering is only 15%, because this layer is fairly deep and it has a strong crust on top of it, and we assume the probability of manifestation given no triggering is only 0.5%, then what we would find is that the probability that this layer triggered, given that no manifestation was observed, is actually 88.5%, and the probability that it didn't trigger is only 11.5%. So one approach that we're thinking about is to put two circles co-located on the same spot, a closed circle with a weighting factor of 88.5% and an open circle with a weighting factor of 11.5%. So that would be one way of doing it, and that would make this point not be a false negative prediction or false positive prediction, right? Another way that we're looking at this is to use a profile-based method. So instead of coming up with a single critical layer to represent the liquefaction manifestation probability for a whole profile, we're using all of the layers in this profile-based method. And then we're coming up with these logistic functions like you see here. This is a function of probability of manifestation of a layer conditioned on triggering of that layer, given the depth to the center of the layer, QC1 NCS, and I sub C. There are other variables we could look at, like ground shaking intensity, factor of safety. There's a lot of different parameters that could be put in here. But then we do the product sum of these logistic functions and raise them to the power of the thickness of the layer. So J and K are indexes that represent a profile and a layer. And then there's some characteristic thickness here. And the functional form that we're using actually is such that if you had a very thick uniform layer and you subdivided it into thinner layers, you would end up with the same probability of manifestation given triggering using this power function. That's why we put the thickness up here instead of down here as one of the logistic variables. So this is actually the result of one of our regressions. So what we do now is come up with the probability that each layer will manifest, and we roll up all those probabilities to get a probability of profile manifestation, and then adjust the coefficients of these logistic functions until we best separate the data. And so that's what we've done. And here's a result that shows a good prediction. This is one that did manifest liquefaction, and we predict a 91% probability of profile manifestation. So you can see the probability of manifestation of the layer decreases with depth because these deeper layers are probably less likely to reach the surface. You also see that the triggering probabilities are low when the I sub C values are high. That would be a clay-like kind of material. So this is a good prediction, a true positive. Then, of course, there also are predictions like this one. This is also in Wu Fang. This is one where we have a 98.4% probability prediction of manifestation, but there was no manifestation. This is another one with a non-susceptible clayey crust on top, so that we need to do a little more work to figure out the effect of that. And then here's one that did manifest, that we predict very low probability of profile manifestation. And this is from, let's see, Ket and the Loma Prieta earthquake. And what you see is that the I sub C values are all pretty high. So this is a profile of all clay-like material. There's nothing in this profile that's sand-like below the water table that would be susceptible to liquefaction. And so we end up with no probability of triggering. And so no probability of manifestation here, very, very low probability of triggering. So this was probably a cyclic failure of fine-grained soils, not a triggering of liquefaction of sand-like soil. And so this framework that we've developed can also be used to work with cyclic failure, cyclic softening of fine-grained soils too. So that's something that we're looking at doing. And in the end, what engineers care about is whether the ground is going to move and not whether it was caused by liquefaction or cyclic softening. So it would be nice to have a single procedure that can combine them. So here's the conclusions. We have this database. There's a lot of field case history and laboratory data in there. You can query the database through, you can access it through the GUI or make your own queries in Jupyter notebooks. We've done some supporting studies, including a K sigma, K alpha study that Kristen Ulmer has been working on. And there was recently a susceptibility workshop that I think Armin will maybe mention. And now we're working on the model development phase and developing models from this, all of this data in the NGL database. So that's it for me. I have a couple extra slides just in case people ask questions.